Yes, good morning, students. So today I will discuss this maximum power transfer theorem. Right? It states that power transfer from the source, power transfer from the source to the load, power transfer from the source to the load is maximum if load resistance is equal to source resistance. Right? That means RL is equal to R Thevenin. So R Thevenin is the source resistance. Right? So let us take one circuit with the help of which we may be able to prove it. Let us say this is your voltage source of the value V1. This is your R source, that means R internal, and here it will be RL. Right? So current going through it, that will be equal to, let us say, IL. Right? So here I want to calculate power across this PL. So power across the load resistance, power across load resistance, that will be given by IL square RL, I square R. Here I is equal to IL. So that means this will be IL square RL. Right. Now from this, if you apply by applying KVL in closed loop, V1 is equal to R IL into R internal plus RL. Right. So from this, IL is equal to V1 divided by R internal plus RL. Right. Now this is the value of PL. PL is equal to power across the load resistance. Now let us suppose this is your equation number 1. This is your equation number 2. Put 2 in 1. Put 2 in 1. Right. So you will get PL is equal to IL square. IL means V1 divided by R internal plus RL, its whole square, into RL. Right. So this will be PL is equal to V1 square divided by R internal plus RL, its whole square, into RL. Right. So this is the value of power across the load in this particular circuit. Now for the condition of maxima, for the condition, let us suppose this is your equation number next 3. For the condition of maxima, by applying condition of maxima for calculation of maximum power across the load resistance, maximum power across the load resistance, right? Differentiate equation 3, differentiate equation 3 with respect to IL, right? We will have to differentiate this equation with respect to IL for calculation of maximum power, right? So, and put it equal to 0. Put it equal to 0, right? So here that means dPL upon dRL. With respect to RL, we will have to differentiate it. dPL upon dRL is equal to 0, right? So here substitute the value of PL. That means d by dRL of V1 upon R internal plus RL, its whole square into RL is equal to 0, right? So this will be d by dRL of V1 square divided by R internal plus RL, its whole square into RL is equal to 0, right? So here V1 is constant. V1 is constant with respect to RL. So V1 may be taken outside. V1 square into d by dRL of RL upon R internal plus RL, its whole square is equal to 0, right? So this V1 square will be moved on the other side and that will become 0, right? So this equation will become d by dRL of RL divided by R internal plus RL, its whole square is equal to 0, right? So now this will be, because in the numerator as well as in the denominator we are getting the same equation. We are getting the equation with respect which is a variable with respect to RL. So this will become the equation of U by V, right? This will become the equation of U by V, and here this will be that d by dt of u by v is equal to v du by dt. I think you must aware with this relation. D by dt of u by v is equal to v du by dt minus u dv by dt upon v square. Right. So here v is equal to r internal plus rl whole square and u is equal to rl. So this will become r internal plus rl its whole square into d by drl of rl minus d upon drl of r internal plus rl its whole square into rl divided by r internal plus rl its whole square and then its square, that will be equal to 0. v du by dt minus u dv by dt upon v square. Right, this is equal to 0. I'm just differentiating this equation with respect to RL, right? Where if you see, I am taking that RL as a U and R internal plus R internal plus RL whole square, that will be equal to V, right? So this is the basic relation by the use of mathematics, right? So here, if you see, if I will cross multiply this on the other side, this will become 0, right? And your equation will become, only numerator will be left, R internal plus RL, R internal plus RL, its whole square into d by drl of RL minus RL into d by drl of R internal plus RL its whole square is equal to 0. Right? I will just cross multiply V, that means R internal plus RL whole square on the other side. Right? So what you will see, I'm just going to solve this equation further. So here R internal plus RL whole square, R internal plus RL whole square into d by drl of RL, that will be 1, right? d by dt of x raised to power n is equal to nx n minus 1, right? So here d by drl of RL, that means it is RL raised to power 1, 1 into RL raised to power 1 minus 1, that will be 1 into RL raised to power 0, fine. So something raised to power 0 is always 1. So that means d by drl of RL, that will be equal to 1, right? So this is into 1, right? You may solve this for your reference, fine. Then after that, minus RL into, see here, this will be d by drl of RL, R internal plus RL base to power 2. So that means that this will be d by dt of u base to power n, that is equal to n u n minus 1 into d by dt of u, right? Because here this R internal plus RL, this will be variable with respect to RL. So that's why I am just taking R internal plus RL as U, right? So here d by dt of R internal plus RL, its whole square, that will be equal to 2 into R internal plus RL, 2 minus 1 power 1. So d by dRL of R internal plus RL, right? I'm just going to substitute this here, RL into differentiation of this, that will be 2 into R internal plus RL into d by dRL of R internal plus RL, right? These are the simple solution by the use of differentiation, right? Now this will be x plus y, right? So we will differentiate both the terms separately. This is equal to 0. So this will be R internal plus RL, its whole square into 1 minus 2RL into R internal plus RL into d by dRL of into d by dRL of R internal plus d by dRL of RL, right? So this will be R internal is constant with respect to RL. So differentiation of the constant, that will be 0, and d by RL of
ਪਾਵਰ ਕਰ ਲਿਆ
Hello.
ਨਾ ਜਿੱਤ ਨਾ
ਵਧੀਆ ਵਧੀਆ ਤੂੰ ਦੱਸ।
ਵਧੀਆ ਕਰ ਮਨਦੀਪ ਔਖਾ ਹੋ ਗਿਆ
ਕਿਹਦੇ ਨਾਲ?
ਰਿਸੈਪਸ਼ਨ ਵਾਲੇ ਨਾਲ
ਕਿਉਂ ਕੀ
ਇੱਥੇ
ਹੋਇਆ?
ਐਡਮਿਸ਼ਨ ਕਰਾਉਣ ਆਏ ਤੇ ਮਨਦੀਪ ਹੀ, ਅੰਕਿਤ ਹੀ ਤੇ ਰੋਹਿਤ ਹੀ,
ਅੱਛਾ
ਤੇ ਕਹਿੰਦੇ ਕਿ ਅਸੀਂ ਐਸੀ ਹੈਗੇ ਤਾਂ ਸਾਨੂੰ ਕੀ ਛੂਟ ਦੋਗੇ? ਅਗਲੇ ਕਾਲਜ ਵਾਲੇ ਕਹਿੰਦੇ 46,000 ਦਾ 46,000 ਰੱਖੋ ਇੱਥੇ। ਤੇ ਕਹਿੰਦਾ ਮਨਦੀਪ ਕਹਿੰਦਾ ਇਹ ਕਹਿੰਦਾ ਪਹਿਲੀ ਵਾਰੀ ਕਰਨੇ ਆ ਕਾਲਜ ਦੇ ਵਿੱਚ, ਡਿਪਲੋਮਾ ਕਰਕੇ ਆਏ ਆ, ਸਾਨੂੰ ਰੂਲ ਨਾ ਸਮਝਾਓ, ਸਾਨੂੰ ਰੂਲ ਸਾਰੇ ਪਤਾ ਵਾ। ਤੇ ਕਹਿੰਦਾ ਜਿਹੜੀ ਸਰਕਾਰੀ ਫੀਸ ਹੈਗੀ ਆ ਉਹ ਲੈਣੀ ਤੇ ਉੱਥੇ ਹੁਣੇ ਦੇ ਦਿੰਦੇ ਆ। ਤੇ ਕਹਿੰਦਾ 46,000 ਅਸੀਂ ਜੇਬ ਚ ਪਾ ਕੇ ਲੈ ਕੇ ਆਏ ਆ। ਉਹਨੇ ਜਿਹੜਾ ਰਿਸੈਪਸ਼ਨ ਤੇ ਬੈਠਾ ਨੀ ਹੁੰਦਾ ਸਾਰੇ ਕੋਈ ਐਨਕਾਂ ਜਾਵਦਾ,
ਆਹੋ
ਉਹਨੂੰ ਕਹਿੰਦਾ ਮਨਦੀਪ ਕਹਿੰਦਾ ਆਪਣੇ ਪ੍ਰਿੰਸੀਪਲ ਨਾਲ ਗੱਲ ਕਰਵਾ ਤੇ ਇਹਨਾਂ ਨੇ ਗੱਲ ਕਰਨੀ ਹੈ।
ਅੱਕੇ ਪਏ
ਕਹਿੰਦਾ ਇਹਨਾਂ ਨੇ ਗੱਲ ਕਰਨੀ ਆਪਣੇ ਹੈ।
ਪ੍ਰਿੰਸੀਪਲ ਸਰ ਨਾਲ ਗੱਲ ਉਹ ਮੈਂ
ਕਹਿੰਦਾ ਪ੍ਰਿੰਸੀਪਲ
ਮੇਰੀ ਗੱਲ ਸੁਣ ਜਿੱਦਣ ਮੈਨੂੰ ਪੁੱਛਿਆ ਕਿ ਮੈਂ ਕਿੰਨੇ ਪੈਸੇ ਡੈਡ ਤੇ ਮੈਂ ਕਿਹਾ
ਹਾਂ
ਮੈਂ ਪੁੱਛਿਆ ਕਿੰਨੀ ਫੀਸ ਆਪਣੀ ਟੋਟਲ, ਕਹਿੰਦੇ ਸੀ 42,800।
ਅੱਛਾ
ਬੁੱਢੇ ਨੇ ਕੱਢਿਆ 42,800 ਮਾਰਿਆ ਕੈਸ਼ ਕਰੋ।
ਮੈਨੂੰ ਅੰਕਿਤ ਦੇ ਫੋਨ ਕਰਕੇ ਕਹਿੰਦਾ ਭਾੜੀਆ ਗੱਲ ਕਰਕੇ ਰੱਖ, ਐਵੇਂ ਔਖੇ ਹੋ ਜਾਂਦੇ ਪਏ। ਮੈਂ ਕੋਈ ਨਾ ਕਰ ਦਿੰਦਾ ਮੈਂ ਸਾਰੀ ਗੱਲ
ਆਪਣਾ
म्यूट कौन कर देंदा बार बार यार?
किन्ने म्यूट किया उस्ताद?
फैजान जी मोहब्बत फैजान जी रहेगा।
की ना उस्ताद दा रुपया काट लेंदे। ओ किथे अजो किथे गया ओए? सतनाम सिंह किदा? और सतनाम है। हेलो
ਵਧੀਆ ਵਧੀਆ ਭਰਾ ਤੂੰ ਸੁਣਾ।
ठीक
भाई
है।
ਅੰਮ੍ਰਿਤਸਰ ਦਾ ਤੂੰ?
ਹਾਂ ਅੰਮ੍ਰਿਤਸਰ ਦਾ ਹੀ ਆ।
ਇੱਥੇ ਆਪਣੇ ਪੰਜਾਬੀ ਚੱਲ
भाई
ਪਈ ਆ
सर
ਨਾ
ने सबको म्यूट करने बोला, म्यूट कर दूं?
ਕਰਦੇ ਕਰਦੇ
भाई चिकन रिकॉर्ड हो रहा है भाई।
अच्छा 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 अच्छा। और रिकॉर्डिंग बंद कर, रिकॉर्डिंग बंद कर, रिकॉर्डिंग तो कर।
चेतन को होस्ट बनाया यार।
मैंने होस्ट बना, रिकॉर्डिंग सब बता देंगे।
फैजान चेतन को बना होस्ट।
Yes. So see here. Now in this case, R internal plus RL its whole square into 1 minus 2RL into R internal plus RL into dy RL of this R internal plus dy drl of RL is equal to 0, right? So this will become R internal plus RL its whole square minus 2RL into R internal plus RL. So dy drl of this, that will be 0, plus dy drl of RL, that will be 1. So 0 plus 1, 1 is equal to 0, right? So this will become R internal plus RL its whole square minus 2RL into R internal plus RL, that will be equal to 0, right? Now this will be from these two parts, we may take R internal plus RL common, right? So this will be R internal plus RL into R internal plus RL, because from this one part will be taken outside, remaining is this minus 2RL is equal to 0. So this part, this will be move on the other side, and that will become R internal plus RL minus 2RL. So that will be minus RL is equal to, this will be move on the other side, 0 by R internal plus RL. So that will be 0, right? 0 divided by something, that will be always 0. So from this, R internal plus RL, R internal is equal to RL. So this is the proof of the maximum power transfer theorem, right? This is the proof of the maximum power transfer theorem, that when R internal is equal to, load resistance, at that time power transfer from the source to the load is maximum, right? Now next is, I want to calculate efficiency at this time period, at the condition of maximum power transfer. What should be its efficiency? and what should be the amount of the maximum power transfer, right? So here see here, what is the PL? PL is equal to IL square RL, right? I had substituted the value of IL. IL is equal to, that will be V1 divided by R internal plus RL, its whole square into RL, right? For maximum power transfer, for maximum power transfer, R internal is equal to RL, substituted here. That means PL maximum, that is equal to V1 upon this RL. I am, instead of this R internal, I am substituting RL. RL plus RL, it's the whole square into V1 square into RL, right? I am taking that square root square of the numerator and denominator separately. Then after that, this PL maximum, that is equal to V1 square divided by 2RL, its whole square into RL, right? 2RL into whole square into RL. So this will become V1 square divided by 4RL square into RL. 1 RL gets cancelled out. Remaining is V1 square divided by 4RL. So this is the amount of the maximum power. PL maximum, amount of the maximum power that will be transferred across the load at the condition of maximum power, that will be V1 square divided by 4RL, right? This is the amount of the maximum power which will be transferred across the load resistance at the condition of maximum power transfer, right? Now I want to find efficiency during this condition, right? So we know that efficiency of any circuit, that will be denoted by eta, fine, and this is equal to output upon input into 100. Now this will be your percentage efficiency, right? So here, this is your circuit. At the start I had taken it like this, V1, then here it will be R internal, and this will be your RL, right? So here, what is the power input? Power input, that will be equal to V1, V into I. So V is V1, I is IL, right? V1 into IL. So IL is equal to, already we had calculated its value, V1 into V1 divided by R internal plus RL, right? So as per the maximum power transfer theorem, R internal is equal to RL. So this will be V1 into V1 divided by 2RL. I am just substituting R internal is equal to RL, right? R internal is equal to RL. So this will be power input, that will be as during the maximum power condition, that will be V1 square in upon 2RL. V1 square upon 2RL, right? So this is your P input, right? And this is your P output across the load. Fine. So substitute both of that value in this equation. P output is equal to V1 square upon 4RL and P input is equal to V1 square upon 2RL, right? So efficiency will become percentage efficiency, that will be equal to V1 square divided by 4RL divided by V1 square divided by 2RL into 100. So that will be equal to 50%. So maximum of 50% of the power, 50% of the power will be transferred from the source to the load, from the source to the load at the condition of maximum power transfer, right? Here we are just deriving two important relation. One is maximum power available across the load, that will be given by this equation V1 square upon 4RL, and second is maximum power transfer across the load from the source, that will be equal to 50% only, right? So if we are transferring, we are supplying input as the 100 watt of the power, then only 50 watt of the power will be available across the load resistance. Rest 50 watt, that will be just consumed across the internal resistance of the source, right? So only 50% of the power that will be transferred from the source to the load at the condition of maximum power transfer. Yes, is it clear? Yes. Steps for calculation of maximum power transfer across the load resistance. Steps for maximum power transfer across the load resistance. Now see here, again in this particular case, if you will see this equation for the output power, that will be equal to V1 square upon 4RL, right? We had already derived this equation. Now the thing is, in case of numerical, how you will going to calculate it, right? So if you will see here, P maximum is equal to V1 square upon 4RL, right? So this is very important that V1 is your Thevenin equivalent voltage. V1 is your Thevenin equivalent voltage and RL is Thevenin equivalent resistance, right? V1 is, again I am repeating, by the use of maximum power transfer theorem, the power across the load may be calculated as this V1 square upon 4RL, right? Here V1 is the V Thevenin and RL is the R Thevenin. So simply you will have to apply Thevenin theorem across the circuit, Thevenin theorem across the circuit, calculate VOC by using the same steps as that of the Thevenin theorem, and calculate R equivalent by applying that short circuit all the voltage sources and open circuit all the current sources. Fine. So here this by applying this, you will get V1 square upon 4RL, where RL is this R Thevenin and V1 is V Thevenin. So by substituting the value of V Thevenin and R Thevenin, you will be able to calculate maximum power across the load resistance. So first of all, any network will be given to you. Instead of that value of RL as 2 ohm to 3 ohm, 5 ohm, some notation will be given to you. That means only it will be represented by RL, right? No magnitude of the RL will be given to you. Fine. So when no magnitude of the RL will be given to you, apply the same steps. That means remove the load resistance RL. Fine. Then after that, short circuit all the voltage sources, open circuit all the current sources. Then apply that simple basics and calculate R equivalent across the load resistance terminal, right? R equivalent across the load resistance terminal. So there you will get that R Thevenin is equal to RL. Fine. So whatsoever value you will get across the this load resistance are equivalent, that is your value of the RL, and after that just calculate VOC by again substituting that again substituting all the energy sources in the network, right? And by applying the basics, that means by applying KCL and KVL, you will be able to calculate VOC across the load resistance terminal, right? So across the load resistance terminal, so that is your value of V1. So V1 is the Thevenin equivalent voltage and RL is the Thevenin equivalent resistance. So by substituting both of that value, you will be able to calculate maximum power as per the maximum power transfer theorem. That means you must be able to calculate VTH and RTH by the use of Thevenin theorem if we want to calculate maximum power transfer across the load as per the maximum power transfer theorem, right? So this is regarding the various steps for calculation the maximum power transfer across the load resistance. So in this network, calculate this is your RL, calculate the current IL in the load resistance of 10 ohm by using Norton theorem, right? So again, step 1 is remove the load resistance, remove load resistance and calculate Rn. Here we are just giving the notation as RTH. Here I am taking the notation as Rn, right? So for Rn, just short circuit all the voltage sources. You see your voltage source 1. So this will be short circuit. From this point, I am just removing that load resistance, and here it will be the resistance of 15 ohm, and this voltage source will be short circuited again. Now this is the network which is having the A and B as the output terminal. So again, you may take that A and B as the outer terminal, and again by the similar methodology, this will be your 5 ohm and 15 ohm. So these two are in parallel. So if you will calculate Rn here, Rn is equal to 15 into 5 divided by 15 plus 5. Right? So 75 by 20. This is your value of Rn. Right? So Rn is equal to 75 by 20 ohm. Right? 75 by 20 ohm. Right? So here Rn will be same as that of the 75 by 20 ohm. Right? Now Rn is the same as that of the previous case because steps will be similar. So that's why not explaining so much, because I had just calculate the same numerical in the previous lecture. So for calculation of Rn, you may refer my previous lecture. Fine. Now, next is I will have to calculate short circuit current, because I want to calculate this with the help of Norton theorem. Fine. So now place next step is place all the energy sources in the circuit again. Right. Place all the energy sources in the circuit again. This will be 5 ohm and 50 volt, and here this will be your open circuit. From this point, I had just removed that load resistance 50 ohm, and here it will be like this is what this is your 100 volt source, right? So I am just taking this across the output, right? Across the output. So what you look at here, this will be your terminal A and B. This is your terminal A and B, and here this will be 5 ohm, and this will be your 50 volt source, and again here this will be 15 ohm and 100 volt source, right? So this is the equivalent circuit of the same, and here I am applying the short circuit. I will have to calculate the current here. That will be ISC. Fine. So for this, I am assuming that this at one time one voltage source is present, right? That is actually the application of the superposition theorem that I will take in next few lecture, after next few lecture, right? So considering 100 volt source first, 100 volt source first, and short circuit second voltage source, that means 50 volt source, right? So this will be short circuit. At one time only consider one circuit. So this is your ISC, right? Here it will be 5 ohm. There, here I am applying the short circuit. Then this will be like 100 volt. Fine. Now see here, these two are in parallel. Here resistance is 0. So R equivalent of these two resistances, R equivalent is equal to 0 into 5 upon 0 plus 5. That means 0 by 5, that is equal to 0. So instead of these two resistances, I am just taking the short circuit only. Whatsoever resistance will be in parallel with short circuit, that will become 0. So then this will be 15 ohm resistance, 15 ohm, and that is, now here I am going to calculate ISC, 15 ohm and 100 volt. So let us suppose this is your ISC dash, right? So here ISC dash is equal to V by R 100 by 15, right? Ampere. Now consider the second source. I'm just drawing it here. Consider the second source. That means now I am just going to apply short circuit across the 100-volt source. So this will become, these two branches may be interchanged in drawing, right? So here this will be 5 ohm and 50 volt, right? And this will be your 15 ohm resistance. This will be short circuit, right? So this 15 ohm in parallel with short circuit, that will become 0. Now the circuit will be like here I am going to calculate ISC double dash due to 50 volt of the source. So here now you will calculate ISC double dash 5 ohm and 50 volt, right? So ISC double dash from this circuit, ISC double dash is equal to 50 by 5. That means this is your 5 ampere, right? So if you see in both of the cases, here ISC dash and here ISC double dash, both are in the same direction, in the downward direction. So that means now ISC total, that will be the sum of ISC dash plus ISC double dash. If these will be in opposite direction, then this will be the subtraction of the two current. So this will become 5 plus 100 by 15. So you may calculate it. This will be the total current I Norton, right? This will be the total current I Norton. Just a minute, I am just going to calculate it. So see, ISC is equal to this 100 by 15, that will be 6.66 plus 5. That means this will be plus 5. So that will be 11.67 ampere, right? 11.67 ampere. This is the total ISC, and that is your value of the I Norton, right? Now in next step, make the Thevenin equivalent or Norton equivalent circuit. Make the Norton equivalent circuit, right? And the Norton equivalent circuit will consist of 3 elements. One is IN, right? Second is RTH or RN, and third is your RL, right? So RL is equal to 10 ohm, RN is equal to 75 by 20 ohm, and IN is equal to 11.67 ampere, right? Here I am going to calculate IL. So IL is equal to IN into RM divided by RN plus RL. Substitute all that value. 11.67 into 75 by 20 divided by 75 by 20 plus 10 ohm. So you may calculate it. This 75 by 20, that is equal to 3.75, right? So this will be 11.67 into 3.75 divided by 3.75 plus 10, 13.75, right? So you may calculate it. Further, so this will be 11.67 into 3.75 divided by 13.75. So this is equal to 3.75 multiplied by 11.67, that will be 43.7625. 43.7625 divided by 13.75, right? So equal to this divided by 13.75. So this will be 3.182. This will be 3.182 ampere, right? So this is your value of IL, and BL is equal to 3.182 into 10. That will be 31.82 volt. So this is your required answer by the use of this Norton theorem. So either you will use that Thevenin theorem or Norton theorem, value of the load current will be same. If your calculation are correct, your value of the load current will be same. So these are two different methodology. These are two different methodology to calculate the load current in one branch or in across one resistance, right? You will get the same result during by using both of the methodology. So this is the end of the lecture. We will meet in next lecture again, right? So if any problem is there, you may ask. Otherwise, in next